Hi, welcome to a podcast on buffers and weak acids. This podcast is just to simply show you how to work two problems and to talk about briefly what a buffer is. A strong acid completely dissociates. And so if you look at H plus and Cl minus, where do they come from in this HCl? There's no HCl flowing in this beaker at all. There's just water liquid and positive ions and negative ions. There's none of this entity here at all. It's a strong acid because it completely splits apart, and all the H ions that are present in this beaker were present in this substance that I put into it. And those are the things like hydrochloric, hydrobromic, H2SO4 sulfuric acid, nitric acid, hydrogen iodide, and perchloric acid. Right? Those are all the strong acids. They completely dissociate. Everything else is weak. And those weak acids do not completely dissociate. So you would see a double arrow, and what would you see? You'd see H plus, and you'd see this negative anion right here. And what do you have floating around in this beaker? This actually is dissolved. It's not dissociated. So you have lots of these, don't you? You have lots of these right here. And you have very few hydrogen ions compared to what you have dissolved as a blob. And you have very few of these negative anions compared to what you have dissolved as a blob. So you don't have any hydrogen ions, then you don't have many hydrogen ions floating around so that they can make a pH. Make sense? Here all the hydrogen ions are present. Everything is completely dissociated. Here's having a difficult time dissociating. So what a buffer does is it complicates matters. This is an acid. I don't know how good of an acid it is. We have to figure it out and find the pH. But now I'm going to complicate issues by adding something else that has this ion. And if I put this ion into this water, what's going to happen? Well, this H and this negative ion right here, they don't like to be dissociated. They'd rather be this compound. Dissolved as a group, right? It's dissolved as a group. So what happens is the equilibrium gets shoved in this direction. I'll show you. It's easier. Okay? So the equilibrium concentration of hydrogen ions in a 1.0 molar solution of HF is 2.7 times 10 to the negative 2 molarity. Find the percent dissociation. That's the first part of this. So I actually should call this A and call this B. Okay? So for A, I need to find the percent dissociation. What is that? That's how many hydrogen ions I have dissolved out of my HF times 100 molarity. Okay, so the first part of this assumes that you've already done an ice problem. And we actually did this in the weak acid, strong acid podcast. So an ice problem was done, and how do you know that? Because this is a weak acid, right? It has an equilibrium concentration. It gives you a Ka later in the problem, so you know it's a weak acid. And so to plug it into that, I'm going to go ahead and I'm going to put 2.7 times 10 to the negative 2 over 1. Those are my molarities, correct? And so if I do that, and I actually did my math, get my calculator, sorry, and I multiply that by 100, right? You get 2.7. Just making sure. It's been a long night. Okay, so it's 2.7% dissociation. And so when you remember we did problems and you ignored X, you wouldn't have to account for that X. You could go ahead and ignore it because it's under the 5% rule. Now, if I wanted to right now, I could figure out what the pH is. Okay, of just plain old HF. So let's just do that to do it, okay? It doesn't ask you to do the problem. I want to show you what happens when I put this buffer in. If I actually do the pH, which is the negative log of that 2.7 times 10 to the negative 2 molarity, I get a pH of 1.56. That's just my HF. Okay, and again, I did an ice problem to find that out. So now I'm going to find the pH of a 1 molar HF solution when I add 1 molar sodium fluoride. So let's stop for a second and think about what's floating around in my beaker. What do you have floating around in your beaker? You have HF floating around your beaker, and that's aqueous. That's a blob. You have very little H and very little F. You have all the 1 molar Na and all the 1 molar fluorine. So how would I depict that? Well, I'd go ahead and write a dissociation equation, right? That's the first thing I always have to do when I have a weak acid. And think about it for a second. If this has a Ka value, that means what? That means I have lots of this and very little of these too. Right? And we know that we have 1 molar and none of this and none of this. So I'm going to go ahead and ice it. Right? Okay. Now, that's what happens if I just have HF. And we did that in a problem. Okay, that's what we did before, and that's how they found out, or we found out the 2.7 times 10 to the negative 2 molarity by plugging in and finding the value using Ka. Now, what's true? Now I have 1.0 molar of this and 1.0 molar of this, right? I had 1.0 molar of this minus X, and X is tiny, isn't it? It's 0.027, or not tiny, but it's small enough. And this is 0.027 molar, and this is 0.027 molar. So what's happening here is I have, let me use a different color. I have, from sodium fluoride, I have 1 molar. Right? Aren't I getting fluorine from this right here? I have 1 molar fluorine. So I'm going to put my 1 molar right here. This 1 molarity is coming from my sodium fluoride, which completely dissociates. I have all Na plus and all F minus. And the Na doesn't matter, because Na has nothing to do with this equation whatsoever. But my fluoride ion is my common ion. Isn't it in common here? So I need to put it in here. And now I don't have 0. Right? Where's the 0 coming from? The 0, in this case, is coming from my HF. I have none of that. Correct? Where's my 1 molar coming from? My 1 molar is coming from my sodium fluoride. Okay? It completely dissociates. Sodium, I don't care about. It's still floating around in there. But I care about this fluorine ion, because this fluoride ion right here is going to combine with my H plus, and it's going to shift my equilibrium back to the left. So that means I need to put it down here as well. Now, I'm going to go ahead and write a Ka, which is 7.2 times 10 to the minus 4th. That's equal to my H plus, and my F minus, and my HF right here. That hasn't changed. It's still my equilibrium expression. But now what's true? Okay? What's true here? I have X for my hydrogen ion. I have X for my HF. And I have 1.0 minus X for my HF, don't I? What do I have for my sodium fluoride? I have 1.0 molar from this, for my sodium fluoride. So now I'm going to go ahead and I'm going to ignore this X. Why am I ignoring that X, guys? Because it's very small, right? We already figured out it's small. It had a 2.7% dissociation, right? It's below 5%, so I can ignore it. Now, I'm also going to ignore this X value. It's small also. Why, where's it coming from? Oh, look, it's coming from my poor dissociator, isn't it? Right? That's my tiny, tiny amount. Or at least tiny amount. So I'm going to go ahead and I'm just going to solve for x. So again, why am I ignoring the bottom part? I'm ignoring the bottom x right here because it's small. It's coming from my poor dissociator. And if you think about it, this x is also small because how much fluorine is being made? Not much, because it's not a good dissociator. So when I go ahead and have these numbers, my value is just going to be 7.2 times 10 to the minus 4th. That's equal to my x, which is equal to my hydrogen ion concentration. Right? Because this 1 over 1 cancels. And if I put that into my negative log, and I take the negative log of my hydrogen ion concentration, which is 7.2 times 10 to the negative 4th, my pH is 3.14. Look what just happened. My pH of just my HF is 1.56. My pH with the buffer is 3.14. So if I don't want this situation to be that acidic, I can actually add a buffer, sodium fluoride, a salt with a common ion, and I can make the pH shift more towards being basic. Maybe I have a stream where the fish eggs need to hatch and it's too acidic and I need to change it. I could shift it. This is what happens in your body and your kidneys and your lungs all the time. So let's try another one, and then I'm done for this podcast. So find the pH of a HCO, so our hydrogen acetate, acetic acid solution, when you add this salt. So what do you know? You're trying to find pH, and you have this acid right here. Is it strong or weak? If you said weak, you're correct. So I'm going to go ahead and I'm going to dissociate it. Acetic acid is going to dissociate, double arrow, into hydrogen ions and acetate ions. What's true? I have 0.5 molar to start with. None of this and none of this. This is going down by x. This is going up by x. This is 0.5 minus x, x, and x. I, C, E. Now, what happens? And by the way, I'm going to find the pH, so do I need to write a Ka expression? Might as well do that now. So you're still doing this the same. You're still dissociating, writing your equilibrium expression, just like we've always done. Plugging your numbers in, your values, x, variables this time, right? And 0.5 minus x. I'm going to go ahead and put my Ka value here. This is actually a smarter way to set it up than I set up the last one. Okay, now, that is if I just do a weak acid problem. What's the deal here? Okay, let me go ahead and use purple, I guess. I have this going on here, don't I? So what's true? If I put sodium acetate into a beaker, I have these two ions because it completely splits apart. Sodium ions and acetate ions. Does sodium have anything to do with the equilibrium expression you see on the board in front of you? No, it does not. These sodium positive ions are going to float next to this hydrogen ion, and they're going to go, get away. You're positive, I'm positive, I don't like you. It's going to float near this, and it's going to go, oh my gosh, I'm going to go ahead and dissociate. Because doesn't water split it apart, right? I don't need to form a compound with you. Water's tearing me apart. And sodium's going to float near this, and it's not going to know what to do at all. There's no interaction. So sodium isn't even part of this. It's still floating around the beaker. It's still a species, but it has nothing to do with what we're talking about. So, what's left? Oops. Sorry about that. So what's left? I have 0.5 molar of this floating around. That's 0.5 molar more than I had to start with. So I'm going to put this 0.5 molar here. Why? Where'd the 0.5 molar come from? It came from my salt. That's my common ion, isn't it? And what happens? What does Le Chatelier tell us? If we increase this in an equilibrium expression, if I increase the concentration, isn't it going to shove the equilibrium in that direction? And what's that mean? That means I have less hydrogen floating around, right? Hydrogen goes down. Isn't this going to go down? And this is going to go up, which means I'm going to have lots more of this, which means if I have less hydrogen ions, then that means I'm actually going to have a change in my pH. So what I need to do is I need to amend what I wrote down here. I need to actually change this, and I need to put my X here from where? From my acetic acid. Plus, I need to go ahead and put 0.5 molar from where? From my nacho, from my sodium acetate. What do you say here? Ignore because small. Okay, why? Because it's coming from a weak acid, so it's having a difficult time dissociating, so there's very little of this floating around. And I'm also going to ignore this, because it's small. Why am I ignoring that? Where's this coming from? Oh, look, it's coming from a bad dissociator as well, so there's very little of it compared to my salt that's now dissociated. Okay, so when I plug those numbers in, I'm going to go ahead and get an X that's equal to 1.8 times 10 to the negative 5. And what is X? Oh, it's my hydrogen ion concentration, so I need to label that molarity. And why is it equal to this? Well, if you get rid of X and get rid of X, don't 0.5 and 0.5 cancel? Okay, now what do I need to find? I need to find the pH. How do I do that? I do negative log of my hydrogen ion concentration. And my pH is going to go ahead and be 4.74. That's my pH. Okay? So that's how you find the pH of a weak acid when you add a common ion. And sometimes they say a buffered solution. That might be the terminology. Containing something, containing a weak acid and its salt with its common ion. Or you just have to look for the fact there's a common ion involved. And you have a key that you have a weak acid. Why do you have a weak acid here? Because right here you have a Ka value that goes with this weak acid. And here's my common ion, right, which is going to compound issues.